Every star you have ever seen is already dying. Physics has known exactly how the universe ends for over a century. And tonight, we are going to walk through every stage of that ending together, one step at a time, all the way to the last light. If you are new here, welcome to Silent Cosmos. Hit subscribe, find somewhere comfortable and settle in, because tonight we are going to follow time itself to its final second. And what physics actually says about how the universe dies is stranger, colder, and more precise than anything you were ever told. Settle in and let's ease into this one slowly. Part 1, the fire has already started. There is a number that most people have never encountered, and it takes a few seconds to absorb once you hear it. The number is 10 to the power of 14. That is a 1 followed by 14 zeros, and it is the rough estimate in years of how long stars like the Sun will be able to form in this universe. 100 trillion years. Your first instinct might be to feel reassured by that. 100 trillion years sounds like forever, the kind of number that lives comfortably outside human concern, the kind of number you can set aside without guilt and return to the business of living. And then you sit with it a little longer and you realize that the number is not the reassuring part. The number is the terrifying part, because the universe is already 13.8 billion years old. We are already in it. The clock is already running, and 100 trillion years divided by the age of the universe tells you something that should stop you cold. We are in the first fraction of the 1% of the era during which stars can form at all. The cosmic morning has barely begun, and it is already fading. Let me say that in a different way. The universe is a fire, not metaphorically, a literal nuclear fire burning across hundreds of billions of galaxies, and that fire is already running out of fuel. The rate at which new stars are forming in the cosmos today is approximately 30 times lower than it was at its peak, roughly 10 billion years ago. The universe built most of its stars early. It was prodigious in its youth. It threw energy into star formation the way a civilization throws everything into building cathedrals, and then it slowed down. The modern universe is a place where old things vastly outnumber new things, where most of the action happened billions of years before any human eye existed to observe it, and where every year that passes is another year in which the universe has slightly fewer resources, slightly dimmer prospects, slightly more of its matter locked away in stellar corpses that produce no light and do nothing but wait. That is the context you need before we can talk honestly about the end. The end of the universe is not a distant, abstract catastrophe. The end of the universe is a process that has already begun. You are inside it right now. The question is simply how long it has left to run and what the final stages look like, and the answers physics gives to those questions are some of the most specific, most precisely calculated, most unsettling facts in all of science. Start with what we actually know, because the confidence with which physics can describe the future of the cosmos is remarkable and worth pausing on. We know the universe is expanding. Edwin Hubble established that in 1929, and a century of increasingly precise measurement has confirmed it to the point where the expansion itself is now used as a calibration tool for other astronomical instruments. We know the expansion is accelerating. That discovery came in 1998 from two independent teams studying distant supernovae led by Saul Perlmutter, Brian Schmidt, and Adam Rees, all three of whom shared the 2011 Nobel Prize in Physics for finding that the universe is not just spreading out, but is spreading out faster and faster over time. And we know that the thing driving this acceleration, the thing cosmologists call dark energy, makes up roughly 68% of the total energy content of the universe, which means dark energy is not a minor player, not a correction term, not a footnote to a simpler picture. Dark energy is the dominant feature of the cosmos. It is the majority shareholder in reality's energy budget, and we do not know what it is. That last sentence is the one that should make you stop. We do not know what dark energy is. Not in the way that we do not know what is inside a black hole, where the mystery is of the exotic and inaccessible variety. We do not know what dark energy is in the much more immediate sense that it constitutes the largest single component of the universe and yet remains without a confirmed physical description at the level of particles or fields or any mechanism that science has been able to identify with confidence. The most honest description of dark energy currently on the table is the cosmological constant, the term Einstein added to his field equations in 1917 to balance the universe, the term he later called his greatest blunder, the term that observations in the 1990s forced us to resurrect as a serious physical entity. The cosmological constant is, in essence, an energy density intrinsic to empty space. It is the pressure of the vacuum, the background hum of the void, the energy of nothing. And that energy of nothing is apparently the most powerful force currently shaping the destiny of the cosmos. Now here is where the picture gets genuinely complicated, and I want to take it slowly because the details matter enormously. The future of the universe does not depend on whether dark energy exists. It exists. We have measured it. What the future depends on is the precise character of dark energy, specifically whether it behaves exactly as a cosmological constant, with a fixed and unchanging energy density, or whether it evolves over time. And as of 2024 and 2025, that question has become the most active and most unsettling open question in all of cosmology. The Dark Energy Spectroscopic Instrument, DESI, has been building the largest three-dimensional map of the universe ever constructed, charting the positions of tens of millions of galaxies across 11 billion years of cosmic history. The first major results from DESI, released in 2024, showed something subtle but deeply significant. When combined with data from the cosmic microwave background and from supernova surveys, the DESI data hints that dark energy may not be a cosmological constant after all. Dark energy may be weakening. The force that has been accelerating the universe's expansion may be losing strength over time, and updated results released in 2025 strengthened those hints rather than dissolving them. Scientists are careful with their language here, appropriately cautious about a claim this large, but the direction of the evidence is increasingly pointing toward an evolving dark energy rather than a fixed one. What that means for the universe's fate, we will discuss in detail later tonight. For now, simply hold this piece of information the way you hold an unresolved chord. Something is there. We are not yet sure what it is telling us. The future is genuinely open in a way it was not 5 years ago. But regardless of how that particular question resolves, the broad outline of the universe's future is not in serious dispute among physicists. The stars will die. Matter will decay. The universe will grow cold. The only question is the exact sequence and the exact timescales, and even those are known to a degree of precision that should astonish you. When physicists say the last stellar remnants will evaporate in roughly 10 to the power of 78 years, that number comes from actual calculations, from actual physics, from equations that have been checked and rechecked and extended by some of the most careful minds our species has ever produced. The number might be wrong in the third decimal place. It is almost certainly correct in its general magnitude. The future is long and it is bleak, and physics has already mapped most of it, and we are going to walk through every stage of it together, starting with where we are. Where we are right now is inside something cosmologists call the stelliferous era. The word stelliferous comes from the Latin for star-bearing, and that is exactly what it describes. The current epoch of the universe is the era in which stars exist. It is the era in which nuclear fusion is the primary energy-generating process in the cosmos, in which matter, organizes itself under gravity into spinning balls of plasma hot enough to fuse hydrogen into helium and thereby release the photons that make galaxies glow and allow life to exist on at least one small planet orbiting a middling star in an unremarkable corner of a spiral galaxy in a cluster that is itself unremarkable by cosmic standards. The stelliferous era began approximately 100 million years after the Big Bang, when the first stars ignited, and it will last until roughly 100 trillion years from now, when the last star will exhaust its fuel and go dark. And we are currently sitting at the 13.8 billion year mark inside an era that spans 100 trillion years, which means we are approximately at year 13 of a 14,000-year-long party. The music is still playing, the guests are still dancing, but the supplies were bought 13,000 years ago and they are running out. What I want you to feel before we move on is not dread exactly, but something more precise than dread. I want you to feel the weight of the time scale, 100 trillion years. To get a grip on it, start with 1 million years, which is roughly the average lifespan of a typical animal species on Earth. Then multiply that by 1 million, that gives you 1 trillion years. Then multiply that by 100, that gives you 100 trillion years. Every lineage of life that has ever existed on this planet, every trilobite and dinosaur and fish and flowering plant and primate and human, all of it combined represents less than a blink within the timescale we are talking about when we talk about the end of the stelliferous era. And that is just the first phase, just the part where stars still shine. The parts that come after are longer, far, far longer. And we are going to spend the rest of tonight walking through each of them because the universe has a story, and the story does not end with the last star. Part 2, where we live and what we cannot keep. You are made of stellar ash. Every atom of carbon in your body, every atom of oxygen in the air you are breathing right now, every iron atom in your blood was forged inside a star that lived and died before the sun existed. The sun itself is a second or third generation star, meaning the gas cloud that collapsed to form it had already been enriched by the deaths of earlier generations of stellar fusion reactors. You are, in the most literal atomic sense, the product of stellar death. And the star that currently warms your planet and powers your biosphere and makes the sky blue during the day is itself in the process of dying, just doing it on a time scale that is almost beyond human comprehension. The Sun is 4.6 billion years old and is approximately halfway through its hydrogen-burning main sequence lifetime. In roughly 5 billion years, it will exhaust the hydrogen in its core. The core will contract and heat up, triggering hydrogen fusion in a shell around the core, and the outer layers of the Sun will expand dramatically as the energy from that shell pushes outward. The Sun will become a red giant, swelling to perhaps 200 times its current diameter, most likely engulfing Mercury and Venus, and possibly reaching Earth. The oceans will boil, the atmosphere will be stripped away, the surface of the planet will melt. Whatever life exists here at that point will either have left or will be erased. This is not speculation, it is the well-understood life cycle of a solar mass star confirmed across thousands of observed stars in various stages of the same process. But here is the thing about the Sun's death that most people miss. The death of the Sun is not the end of the Sun. After the red giant phase, the Sun will shed its outer layers in a planetary nebula, and the remaining core, stripped of its envelope, will be left behind as a white dwarf. A white dwarf, roughly the size of Earth, but containing roughly half the mass of the original star, composed primarily of carbon and oxygen, glowing not from fusion, but from residual thermal energy, slowly radiating its heat into the surrounding darkness over billions of years. The Sun will die as a star and become a white dwarf, and it will then spend trillions of years quietly cooling, and eventually it will fade to an object we have never directly observed anywhere in the universe, because the universe has not been around long enough yet for any white dwarf to have fully cooled. The theoretical endpoint of a cooling white dwarf is something called a black dwarf, a cold, dark, inert lump of crystallized carbon and oxygen, no longer distinguishable from the empty space around it except by its gravity. The universe does not yet contain a single black dwarf. They are objects that belong to the far future, to time scales that dwarf the current age of the cosmos. This is actually a useful point to anchor yourself to as we go forward. The universe is 13.8 billion years old. That sounds old. That is old by human standards, by geological standards, by the standards of anything that lives and breathes on a planet. But it is not old by the standards of what the universe will eventually become. The universe in its current state, full of glowing stars and active galaxies and the faint warmth of the cosmic microwave background, is the universe in its youth. It is the universe in its brief, bright, prodigal period of energy expenditure. And almost every process we are about to discuss will happen on timescales that are not millions or billions of years longer than the current age, but trillions and quadrillions and googles of years longer. The current age of the universe, 13.8 billion years, is so short compared to the timescales of the universe's future that it functions as a rounding error, a zero before the decimal point. Here is one more piece of context before we step forward through time. The universe is currently full of about 2 trillion galaxies, not 2 trillion stars. 2 trillion galaxies, each containing anywhere from 100 million to several hundred billion stars, each star potentially hosting planets, each galaxy containing more stellar material than any human mind can hold without collapsing into abstraction. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, and in each of those galaxies right now, stars are being born from collapsing clouds of gas and dust, living out their luminous lives, fusing hydrogen and helium and carbon and all the heavier elements in the periodic table, and eventually dying and enriching the surrounding interstellar medium with the products of their fusion. It is an extraordinary, improbably rich machine, the stelliferous era, and it has been running for 13 billion years, and it has approximately 86 trillion years left to run. And then it will stop. The mechanism by which the stelliferous era ends is straightforward. Stars form from clouds of gas, primarily hydrogen, and helium. They burn through that gas, converting it via fusion into heavier elements. Some of that gas is eventually ejected back into the interstellar medium through stellar winds and supernovae, where it can be recycled into new stars. But the recycling is not perfect. Every generation of stars locks some fraction of its mass up in stellar remnants, white dwarfs and neutron stars and black holes that cannot be recycled. The total reservoir of star-forming gas in the universe is being depleted with every generation of stars, and the rate of star formation has been declining for billions of years already, as we established. By the time we reach 100 trillion years from now, the available gas will be so thoroughly consumed and locked away that the last generation of stars will have formed, and the ones that remain will be burning through their last reserves. One by one, the lights will go out. Not dramatically, not all at once, but in a slow, statistical thinning, a cosmic dimming, a progressive and irreversible darkening of the sky. The last stars to die will not be stars like the sun. The last stars to shine in the stelliferous era will be red dwarf stars, the smallest, coolest, most fuel-efficient class of stars. Red dwarfs can be as small as 8% of the sun's mass, just barely above the threshold required to sustain hydrogen fusion. They burn so slowly and so efficiently that a single red dwarf can shine for trillions of years. The most common type of star in the Milky Way today is Proxima Centauri, the closest star to the Sun, a red dwarf that has been shining for 4 billion years and has trillions of years of fuel remaining. The red dwarfs are the universe's last candles. They will be burning long after every star like the Sun has gone through its entire life cycle. And when the last red dwarf exhausts its fuel and fades, it will mark the end of an era in the universe's history. The stelliferous era will be over. The universe will never again contain a burning star, and we will need an entirely different vocabulary to describe what happens next. Part 3, after the last fire. Imagine standing outside on a perfectly clear night on Earth, the kind of night you can only find far from city lights in a desert or high mountains, and looking up at a sky blazing with more stars than you can count. Now imagine that same night sky, but instead of a few thousand visible stars, what you see is one star, just one, a faint red point of light in a sky otherwise completely black. Then imagine that light going out, the last red dwarf crossing its threshold into cold collapse. That is the moment the stelliferous era ends, and what comes after is not darkness in the simple sense, not a sky with nothing in it, but something more interesting and in some ways more terrible. The era that follows the stelliferous era is called the degenerate era, and it spans an almost incomprehensible range of time, from roughly 100 trillion years after the Big Bang to perhaps 10 to the power of 40 years, which is 10,000 million years after the Big Bang. In comparison to that number, the entire current age of the universe, 13.8 billion years, is less than the width of a single atom compared to the diameter of the observable universe. The degenerate era is not a transition or an interlude. It is a geological age so long that calling it vast is nearly an insult to the concept of vastness. And during this entire era, the universe is populated not by stars but by the stellar corpses that stars leave behind. The most common object in the degenerate era will be the white dwarf. Today, the universe contains relatively few white dwarfs compared to the total number of stars. But as the stelliferous era progresses and stars continue to exhaust themselves, white dwarfs will accumulate. By the time the last red dwarf fades, the universe will contain a truly enormous population of them, cold, inert, slowly crystallizing remnants of everything that once burned. There will also be neutron stars, the dense remnants left behind by supernova explosions, objects packing roughly 1.5 solar masses into a sphere about 20 kilometers across, so dense that a teaspoon of neutron star material would weigh roughly 100 million tons on Earth. And there will be black holes ranging from stellar mass black holes a few times heavier than the Sun to the supermassive monsters at the centers of galaxies that can be billions of solar masses in size. And there will be brown dwarfs. Brown dwarfs are objects that formed like stars, but never had quite enough mass to ignite sustained nuclear fusion. They glow faintly from the heat of their gravitational contraction, slowly cooling over trillions of years, becoming darker and colder. During the degenerate era, brown dwarfs will outnumber every other class of objects. They are the universe's most patient failures, almost stars that can only wait. In the degenerate era, these remnants will be the universe's primary inhabitants. They will form sparse, dark galaxies, still bound together by gravity but no longer illuminated by fusion. The galaxies will look nothing like the brilliant star-strewn spirals and ellipticals of today. They will be dark, cold agglomerations of inert objects, invisible except by their gravity, scattered across an expanding space that is growing emptier with every eon. Gravity will still be organizing them, still pulling stellar remnants into interactions, still occasionally producing collisions when white dwarfs or neutron stars fall together. Occasionally, two white dwarfs will collide, producing a brief, spectacular thermonuclear explosion, a type of supernova triggered not by the collapse of a single massive star, but by the merger of two dead stars. These will be among the brightest events in the degenerate era, and they will be lonely, separated from one another by incomprehensible stretches of empty time. Now, there is one physical process in the degenerate era that deserves particular attention because it is both deeply counterintuitive and deeply important to what comes after. That process is proton decay. Standard particle physics, the framework we call the Standard Model, treats protons as stable. A proton in the nucleus of an atom has no known mechanism by which it can spontaneously decay into lighter particles. And yet, most extensions of the Standard Model, the theoretical frameworks physicists have developed to try to unify the fundamental forces of nature, predict that protons are not actually stable. Grand unified theories, the class of models that attempt to merge the electromagnetic, weak and strong nuclear forces into a single framework at high energies, generally predict that protons should eventually decay, with lifetimes that are very long but finite. Current experimental lower bounds on the proton lifetime place it at greater than 10 to the 34 years. Experiments deep underground, detectors shielded from cosmic rays and filled with tens of thousands of tons of pure water or other materials, watch for the signature of a spontaneous proton decay and have never seen one. But that experimental lower bound of 10 to the 34 years is entirely consistent with grand unified theory predictions that range up to 10 to the 39 years or higher. If protons decay, the implications for the degenerate era are profound. Every atom, every molecule, every piece of solid matter that exists anywhere in the universe is made of protons and neutrons. Neutrons bound inside atomic nuclei are stabilized by the nuclear environment and would decay only via the same mechanism as protons if proton decay is real. Which means that every white dwarf, every neutron star, every brown dwarf, every piece of rock, every grain of dust is made of material that will eventually fall apart. Not quickly, but eventually. The timeline for proton decay, if it occurs at the rate predicted by the simplest grand unified theories, would reduce all ordinary matter to a dispersed cloud of electrons, positrons, neutrinos, and photons over timescales of roughly 10 to the 37 to 10 to the 40 years. The degenerate era ends when proton decay completes. When the last ordinary matter dissolves into lighter particles, the era of degenerate stellar remnants is finished, and what is left will be primarily black holes. And then there is an additional wrinkle that emerged from research published in 2023 and extended in 2025, work by Heino Falke, Michael Wondrak, and Walter van Zwijlecom at Radboud University in the Netherlands. These researchers showed that a process similar to Hawking radiation, the quantum effect by which black holes slowly emit thermal radiation and lose mass, should apply not just to black holes, but to all massive objects in the universe. White dwarfs, neutron stars, brown dwarfs, even ordinary objects like the Moon, all of them radiate energy via this mechanism, though at rates so slow that the effect is completely negligible on any time scale shorter than cosmological. Their calculations showed that neutron stars and stellar mass black holes evaporate on roughly the same timescale, around 10 to the 67 years, because black holes partially reabsorb their own radiation. White dwarfs would take around 10 to the 78 years to completely evaporate, and the full evaporation of the universe's stellar remnants through this process would be essentially complete at around 10 to the 78 years from now. This is much shorter than previous estimates that placed the evaporation of the universe at 10 to the power of 1100 years. The universe, it turns out, decays faster than we thought. Even that faster timeline is, of course, impossibly remote by human standards, but the physics is real, and it means the degenerate era ends not in an explosion or a crunch, but in a slow, quiet, almost infinitely patient dissolution of everything that matter was. Part 4, the black hole era. When the degenerate era ends, what remains is simpler and stranger than anything that came before. The universe enters what cosmologists call the black hole era. This is the epoch in which black holes are the primary surviving objects, the dominant features of a cosmos that has by this point been expanding for timescales that make the current age of the universe seem like the tick of a clock. Most ordinary matter is gone. The stellar remnants have decayed. What remains are black holes of various sizes, from the stellar mass objects left behind by supernova explosions to the supermassive monsters that lurked at the centers of galaxies for most of cosmic history. The black hole era begins roughly around 10 to the 40 years after the Big Bang, assuming proton decay has completed or at least swept away most ordinary matter by that point, and it extends to perhaps 10 to the 100 years, which is the approximate timescale on which the largest supermassive black holes, those with masses of hundreds of millions or billions of solar masses, would completely evaporate via Hawking radiation. That range, from 10 to the 40 to 10 to the 100 years, spans a stretch of time so vast that the entire previous history of the universe from the Big Bang to the degenerate era fits within its first moment in any meaningful relative sense. Hawking radiation deserves careful explanation here because it is one of the most remarkable and best attested theoretical predictions in modern physics, even though it has never been directly detected. The mechanism was worked out by Stephen Hawking in 1974 and published in 1975. It arises from the intersection of quantum mechanics and general relativity in the extreme environment near a black hole's event horizon. The event horizon is the boundary of the black hole, the surface beyond which nothing, not even light, can escape. In classical general relativity, a black hole is perfectly black. Nothing comes out. But in quantum mechanics, the vacuum of space is not empty. It is a seething sea of virtual particle pairs, particles and antiparticles that spontaneously arise from the quantum uncertainty and then almost immediately annihilate each other, with the borrowed energy being repaid to the vacuum. Most of the time, this process goes unnoticed because the particle pairs annihilate before they have any macroscopic effect. But near an event horizon, something different can happen. One member of a virtual pair can fall into the black hole before annihilation occurs. The other member, suddenly freed from the obligation to annihilate with its partner, becomes a real particle and escapes into the surrounding space. The black hole has effectively emitted a particle at the cost of slightly reducing its own mass. This is Hawking radiation. It is thermal, meaning it has the same statistical distribution as radiation from a hot object. A black hole has a temperature, and smaller black holes have higher temperatures. A stellar mass black hole, one roughly 3 times the mass of the Sun, has a temperature of about 60 billionths of a Kelvin above absolute zero, which is so cold that the black hole would absorb more energy from the cosmic microwave background than it emits, meaning it actually gains mass rather than losing it in the current universe. But as the universe expands and cools, the temperature of the cosmic microwave background drops. In the far future, once the background temperature has fallen below the Hawking temperature of even the largest black holes, those black holes will begin to lose mass via radiation faster than they gain it. The evaporation begins. It is slow at first, almost undetectably slow, but it is irreversible. A black hole losing mass gets hotter. Getting hotter, it radiates faster. It enters a runaway process that ends with a spectacular final explosion as the black hole's remaining mass is converted entirely to thermal radiation in a last burst of Hawking radiation and then simply ceases to exist. For a stellar mass black hole, this process takes roughly 10 to the 64 years. For a supermassive black hole with the mass of billions of suns, it takes on the order of 10 to the 100 years. Those are the timescales of the black hole era. And during this entire era, the universe is not dark and empty in the simplest sense. Hawking radiation means every black hole is a faint, incredibly dim source of thermal radiation. Each black hole glows, not visibly, not in any wavelength detectable by biological eyes or any detector we could imagine building from the remnants of ordinary matter, but physically, thermodynamically, genuinely glowing. The black hole era is a universe full of dim, cooling, very slowly evaporating gravitational furnaces scattered across expanding space, each one converting its accumulated mass into a slow trickle of thermal radiation, emitting toward an ending that they cannot escape. When the last supermassive black hole evaporates, the last particle of the last formerly stellar, formerly galactic structure disappears, there is a final burst of radiation, and then the universe contains nothing but that radiation, nothing but photons and low-energy particles spreading outward through an expanding space that is larger than anything from our current perspective could describe. The black hole era ends, the universe enters its final state. Part 5. Heat death and what comes after silence. The final state of the universe, assuming dark energy remains constant and the expansion continues forever, is what physicists call heat death, or sometimes the Big Freeze. The name heat death comes from thermodynamics and is in a sense counterintuitive because the universe in this state is not hot. It is cold. The heat death refers not to temperature but to the thermodynamic state of maximum entropy, a state in which no further work can be done, no energy can be extracted, no ordered processes can occur, because everything has equilibrated to the same temperature. In thermodynamics, heat can only do work when it flows from a hotter region to a cooler region. When everything is at the same temperature, there is nowhere for heat to flow, no temperature gradient, no work, no processes. The universe has reached thermodynamic equilibrium. The temperature of this final state is not absolute zero. It is a very specific, small positive value set by what physicists call the de Sitter temperature, the temperature of the quantum vacuum in an exponentially expanding universe dominated by a positive cosmological constant. That temperature is extraordinarily small, approximately 10 to the negative 30 Kelvin, but it is not zero. It cannot be zero because the cosmological constant imposes a kind of quantum noise on empty space, a minimum irreducible thermal fluctuation. The universe in heat death is not perfectly cold and perfectly silent. It is almost perfectly cold and almost perfectly silent, vibrating at a temperature so low that it is practically indistinguishable from absolute zero, but is, in the strictest thermodynamic sense, not quite there. What exists in the universe at heat death? After all the black holes have evaporated, after all the Hawking radiation has spread and cooled and diluted across an expanding space, the universe is a cold, thin gas of photons and low-energy leptons, primarily electrons, positrons, and neutrinos. The density of this gas is almost zero. The temperature is almost zero. The photons have been redshifted by the continuing expansion to wavelengths so long that they carry almost no energy individually. There are no galaxies, there are no stars, there are no planets, no atoms, no complex molecules, no structures of any kind. Just this cold, dilute, featureless fog expanding forever through a space that itself becomes progressively emptier and colder. Will anything happen in the universe at heat death? In the strictest classical sense, no. But here is where Boltzmann's statistical mechanics introduces something disturbing. If the universe persists for long enough, and in the heat death scenario, it does persist, it expands but it does not end, then random quantum fluctuations will occasionally produce local deviations from the maximum entropy state. These fluctuations are overwhelmingly likely to be tiny, brief, meaningless ripples in the thermal background. But given enough time, and in a heat death scenario, the universe has literally unlimited time, fluctuations of any size will eventually occur, including, in principle, a fluctuation that momentarily assembles something complex, including, in principle, a fluctuation that assembles a functioning brain with false memories and a momentary experience of existence before dissolving back into thermal noise. This is the Boltzmann brane problem, which we encountered briefly earlier, and which is worth confronting directly here. The universe in heat death will, if the equations are right, eventually produce random configurations of any complexity given unlimited time, including observers, including minds with apparent memories of pasts that never happened, experiencing a moment of consciousness in an otherwise dead universe. The Boltzmann brane problem is not a prediction that the universe is kind or interesting. It is a prediction that the universe is so old and so indifferent that even the most improbable configurations will eventually arise purely by random fluctuation. And that is, when you really sit with it, one of the most vertiginous implications of a universe without an end. Now I want to pause here because the picture we have been building, the stelliferous era, followed by the degenerate era, followed by the black hole era, followed by heat death, is based on a specific assumption. It is based on the assumption that dark energy is a cosmological constant, that it has a fixed, unchanging energy density, and that the universe's expansion will therefore continue forever, accelerating but never reversing, spreading the matter and energy of the cosmos across ever vaster volumes until nothing can ever interact with anything again. That is the most widely accepted scenario, but it is not the only scenario. And the events of 2024 and 2025 have made the alternative scenarios considerably harder to dismiss. Part 6. Dark energy is changing and nobody knows why. In the spring of 2025, at the American Physical Society's Global Physics Summit in Anaheim, California, the Dark Energy Spectroscopic Instrument Collaboration presented their second major data release, and the physics world did something unusual. It paused. The results were described by one of DESI's own scientists as deeply intriguing, and the word intriguing in that context is doing a lot of work. The DESI collaboration had spent years mapping the distribution of galaxies across cosmic time using a technique that relies on ancient pressure waves in the early universe, called baryon acoustic oscillations, as a kind of cosmic ruler. These oscillations, frozen into the distribution of galaxies, have a known characteristic scale, which makes them a reliable yardstick for measuring how the universe has expanded at different epochs. And what DESI found, when they used that yardstick to measure the expansion rate across 11 billion years of cosmic history, was that the data fits a model in which dark energy is weakening over time. Not dramatically, not by an amount that overturns everything, but consistently in a direction that is increasingly hard to explain away as a statistical fluctuation. The implications of weakening dark energy are enormous. Dark energy is the thing that is accelerating the universe's expansion. If dark energy weakens, the acceleration slows. If it weakens enough, the acceleration could stop. And if dark energy does not merely stop but reverses sign, going from a repulsive force to an attractive one, then gravity eventually wins the long-running tug-of-war between expansion and collapse, and the universe does not end in an eternal cold expansion, but begins to contract. Everything that has been moving apart for billions of years begins, slowly at first, and then faster, to move back together. The galaxies stop receding and begin to approach. The voids between galaxy clusters begin to close. The structure of the cosmos begins to reverse, like a film played backward, until every galaxy, every stellar remnant, every black hole is converging on a single point, and the universe ends, not in cold silence, but in a hot, dense crunch, a mirror image of the Big Bang. Cornell physicist Henry Tai published a study in 2025 in the Journal of Cosmology and Astroparticle Physics, suggesting that the universe may have a total lifespan of roughly 33 billion years, with a maximum size reached about 11 billion years from now, followed by a contraction and a big crunch approximately 20 billion years in the future. His model is based on the hypothesis that the cosmological constant is negative rather than positive. which the DESI data does not rule out at current precision. This is explicitly a minority view. Most cosmologists do not yet believe the Big Crunch is the likely outcome, but it is no longer the obviously ruled out scenario it appeared to be 5 years ago. The data is speaking, and what it is saying is uncertain enough to keep everyone honest. I want to be careful here the way I would want any scientist or educator to be careful about not overstating what the DESI results mean. The evidence is suggestive, the indications are strengthening, but they are not conclusive. Scientists involved in DESI itself have explicitly stated that it is too early to claim categorically that dark energy is evolving. Other explanations for the slight tension in the data have not been definitively ruled out. What the DESI results do, unambiguously, is widen the space of possible futures for the universe in a way that was not true before the instrument was built. The clean, confident, cosmological constant equals Big Freeze picture has become genuinely uncertain. And that uncertainty is itself a profound fact about the current state of cosmological knowledge. We do not know what dark energy is. We are not certain what it is doing over time. And the fate of everything depends on the answer. There is a parameter that physicists use to characterize dark energy called W, the equation of state parameter. It describes the relationship between the pressure and energy density of dark energy. If W is exactly -1, dark energy is a cosmological constant and the universe ends in heat death. If W is less than -1, dark energy is what physicists call phantom energy, growing stronger over time rather than weaker, and the universe ends not in a slow freeze but in a sudden, violent tearing apart of everything. If W is greater than -1, but dark energy is not constant, dark energy could weaken and eventually reverse, leading to a big crunch. Current measurements place W very close to -1, but the error bars are significant. The DESI data, combined with other measurements, suggests W may be evolving, starting somewhat above -1 and moving toward more negative values over time. This particular evolution would suggest dark energy getting stronger, potentially pointing toward a universe that ends not in heat death, but in the Big Rip. Part 7, the Big Rip and what it would feel like to be there. The Big Rip is the darkest of the dark endings. It is the scenario in which dark energy does not merely continue but intensifies, growing stronger with every passing moment, until the repulsive pressure of empty space overwhelms every other force in the universe, dismantling every structure that has ever existed, starting with the largest and working its way down to the smallest, until even the subatomic particles themselves are torn apart. If the Big Rip is the universe's fate, it will be not a cooling, but a shattering, not a fading, but a catastrophic dissolution that proceeds through every scale of reality on a precise and calculable schedule. The physicist Robert Caldwell coined the term phantom energy in 2002 to describe the specific form of dark energy that would drive a Big Rip. In phantom energy, the energy density of empty space does not remain constant but grows over time as the universe expands. This is deeply counterintuitive because in most physical systems, diluting a substance by expanding its container reduces its density. But phantom energy is characterized by an equation of state parameter W less than -1, meaning it has properties that no ordinary substance possesses, including negative kinetic energy, which has no classical analog. It is, in the most precise sense, exotic. Whether phantom energy actually exists is an open question that the DESI results and other measurements will help resolve over the coming decade. But imagine for a moment that it does. Imagine that dark energy is phantom energy, growing stronger at a rate that can be precisely calculated from the measured value of W. The timeline for the Big Rip can then be worked out, and it depends critically on the exact value of W. If W is around -1.5, for example, the Big Rip would occur on a time scale of roughly 20 billion years from now. Other values of W give longer or shorter timescales. But the structure of the scenario is always the same. It begins gently. Dark energy is already winning the competition against gravity on cosmological scales today, accelerating the universe's expansion, pulling galaxy clusters apart from each other over billions of years. In a Big Rip scenario, this process intensifies. Galaxy clusters first separate, then individual galaxies are torn from their local groups. Then galaxies themselves are pulled apart, their stars scattered by the increasing strength of dark energy acting on galactic scales. As the Big Rip approaches, the time scale on which dark energy tears structures apart becomes shorter and shorter. Billions of years before the rip, galaxy clusters dissolve. Millions of years before, individual galaxies fragment. Thousands of years before, solar systems are pulled apart, planets torn from their stars, moons torn from their planets. Hours before the final moment, the sun itself would be ripped apart by the expansion of space acting on stellar scales. Minutes before, the Earth would be torn to pieces. Seconds before, every atom in the universe would be stretched past the point where nuclear forces can hold nuclei together, and protons and neutrons themselves would be ripped from their atomic nuclei. And in the final fractions of a second, the fundamental particles themselves, quarks held together by the strong nuclear force inside protons and neutrons, would be pulled apart, and all the matter in the universe would dissolve into a sea of unbound fundamental particles in an instant of cosmic dissolution. Let me say what comes after that, because the Big Rip has a final moment that physics does not fully know how to describe. The instant in which space itself is torn apart, in which the expansion of the universe reaches infinite speed, is a singularity, a place where the equations break down. It is like the Big Bang in reverse, a moment of infinite density and curvature, a boundary beyond which the physics we currently understand cannot see. What happens at the Big Rip singularity is genuinely unknown. It might be the end of everything. It might be the beginning of a new cycle. It might be a transition to a state that requires a theory of quantum gravity to describe, a theory we do not yet have. The Big Rip is not, in that sense, a clean ending. It is a clean ending for everything up to the singularity, and then a question mark. And question marks at the boundaries of space-time are among the most honest and most disturbing features of the physics of cosmology. Part 8. The quiet annihilation nobody talks about. There is an ending more sudden and more total than any we have discussed so far, and it requires no exotic dark energy, no phantom energy, no Big Rip, no big crunch. It requires only that the universe is not currently sitting in its lowest possible energy state, which is a question that particle physics has been quietly struggling with for decades. The scenario is called vacuum decay, or false vacuum collapse, and if it occurs, there is no warning, no precursor, no measurement any civilization anywhere in the universe could have made that would have predicted it or protected against it. The idea begins with the quantum field theory description of empty space. In quantum field theory, the vacuum is not empty. It is a field configuration, a specific state of all the quantum fields that pervade space, and it has an energy associated with it, the vacuum energy. The vacuum we currently inhabit is stable, or at least it appears to be, in the sense that it has persisted for 13.8 billion years without decaying. But the question that theoretical physicists have been wrestling with is whether this stability is absolute or merely apparent. Whether our vacuum is the true ground state of the universe, the lowest possible energy configuration of the fields that make up reality, or whether it is a false vacuum, a local minimum in the energy landscape of the fields, stable enough to have lasted this long, but not the absolute bottom. The discovery of the Higgs boson at CERN in 2012, combined with precise measurements of its mass of approximately 125 giga-electron volts, gave physicists a way to address this question quantitatively. The mass of the Higgs boson determines the shape of the potential energy of the Higgs field, which in turn determines whether our vacuum is stable, metastable, or unstable. When the calculation was performed, the result was genuinely unsettling. The measured value of the Higgs mass combined with the measured value of the top quark mass places our vacuum in a region of parameter space that physicists call metastable. Our vacuum appears to be a false vacuum, a local minimum in the energy landscape, not the absolute minimum. There is apparently a lower energy state available to the universe. We are sitting in a quantum mechanical pocket that has not yet found its way to the bottom. If this metastable interpretation is correct, then there is a non-zero probability per unit volume per unit time that a quantum fluctuation somewhere in the universe will be large enough to kick a small region of space over the barrier and into the lower energy state. That region, once it has tunneled into the true vacuum, will expand at the speed of light in all directions, growing as a bubble of true vacuum spreading outward through the universe. Inside the bubble, the laws of physics are different. The constants of nature take values appropriate to the true vacuum rather than our current false vacuum. The masses of particles, the strengths of forces, the entire physical landscape of reality is rewritten inside the bubble. Outside the bubble, in the false vacuum we currently inhabit, nothing has changed, nothing looks different, there is no warning, nothing to feel. The bubble wall, expanding at the speed of light, cannot be detected before it arrives because no signal can travel faster than the wall. And when the bubble wall passes through you or through the atoms that used to be you, the transition is instant and total. The atoms that made up your body are replaced by the different physics of the true vacuum, which may not support the existence of atoms at all. Everything familiar is erased, not by heat or gravity or tearing, but by a phase transition in the fundamental nature of reality itself. The timescale for vacuum decay is unknown. It could have already happened somewhere in the universe, and the bubble could be expanding toward us at the speed of light right now, with no possible warning. It could be something that happens only once in every 10 to the power of 500 years, making it essentially impossible in any human timescale or even on cosmological timescales. The calculation of the tunneling rate requires extremely precise values of fundamental constants, particularly the Higgs mass and the top quark mass, and current measurement uncertainties are large enough that the result could be anywhere from imminent to essentially never. What is known is that vacuum decay, unlike every other ending we have discussed, would be instantaneous and total. It would not proceed through stages. It would not leave any remnant. It would not allow any structure, however briefly, to survive. If vacuum decay happens, that is the end. Not the end of complex structures, not the end of stars, the end of physics as we know it, replaced by something we cannot predict because we have not, by definition, experienced it. Physicist Sidney Coleman worked out the mathematics of vacuum decay in the 1970s, and the picture he described has been refined and extended by many subsequent researchers. The possibility is not taken lightly. It is a genuine cosmological concern, and the measurements coming from particle physics experiments like the Large Hadron Collider at CERN are in part an attempt to better constrain the parameters that determine whether we live in a stable or metastable vacuum. The answer is not yet in. Part 9. If the universe were to crunch. Let us return to the possibility that dark energy is weakening, because if the DESI hints are correct, and dark energy is an evolving field rather than a constant, the Big Crunch becomes not just a historical curiosity, but a live candidate for the universe's fate. And the Big Crunch is worth understanding in its own right, not just as an ending, but as a physical process with its own structure and its own implications. The Big Crunch is in some sense the most intuitive of the universe's possible endings. It is the scenario in which gravity wins. In the early days of cosmology, before the discovery of dark energy in 1998, the Big Crunch was actually considered the default scenario by many physicists because the early theoretical treatments of the universe favored a closed geometry, one in which the total energy density exceeded the critical value needed to halt and reverse the expansion. We now know the universe is very nearly flat with a total energy density very close to the critical value, but the presence of dark energy made the expansion not just continue, but accelerate, seemingly ruling out the Big Crunch for good. It was dark energy that changed the consensus from Big Crunch to Big Freeze. And now, tantalizingly, the DESI data suggests that dark energy may not be as permanent or as dominant as we thought. If dark energy weakens and eventually reverses, the expansion of the universe slows. First, the acceleration stops. The universe still expands, but at a decreasing rate. Then the expansion itself stops. There is a moment, a maximum size for the universe, after which everything begins to move back together. The recession of galaxies reverses, redshift becomes blueshift. Distant galaxies, which have been invisible to us for billions of years because they have crossed our cosmological event horizon, begin to reappear as the universe contracts and shrinks back into view. The cosmic microwave background, which has been cooling and redshifting for 14 billion years, begins to blueshift and reheat as space compresses the photons together. The Big Crunch plays out roughly as the Big Bang in reverse, though not perfectly. The universe collapses inward. Matter that has been spread across immense volumes begins to converge. Galaxies approach each other and merge. The sky grows brighter as the cosmic microwave background blue shifts into the infrared, then the visible, then the ultraviolet. Stars that have long since died are still present as stellar remnants, white dwarfs and neutron stars and black holes, and these begin to converge along with all the dark matter in the universe. The temperature of the universe rises, matter is compressed. As compression continues, the black holes that have been growing for the entire history of the universe begin to merge with each other, with stellar remnants, with gas clouds reheated by the increasing background temperature growing into cosmic monsters that dominate the final stages of the collapse. In the final moments of the Big Crunch, physics enters territory that general relativity alone cannot describe. As the density of the universe approaches the values at which quantum gravitational effects become important, the smooth continuum of space-time that general relativity assumes breaks down. What happens at the singularity, the point to which the Big Crunch leads, is not known. It might be a genuine termination, an actual ending of space and time. It might be a transition to a quantum gravitational regime from which a new phase of expansion emerges, a big bounce like the one predicted by loop quantum gravity models, in which our entire visible universe is just one oscillation in an endless series of expansions and contractions. It might be something that requires theoretical physics we do not yet possess to understand. The Big Crunch, like the Big Rip and like vacuum decay, ends at a question mark. But there is one feature of the Big Crunch that distinguishes it from the other endings in a way that is, depending on your disposition, either alarming or interesting. The Big Crunch, if it happens on the timescale suggested by Henry Tye's 2025 model, roughly 20 billion years from now, would be relatively soon by cosmological standards. Not soon enough to affect any human being, not soon enough to affect the Sun, which would still have billions of years of hydrogen left to burn, but soon enough that the Milky Way and Andromeda would still be merging, that the local group of galaxies would still be a coherent structure, that the cosmic web of filaments and voids would still be recognizable as such. The universe would end not in the cold, dark, empty futurity of the heat death scenario, but in a state that still retained some of its current structure, compressed and heated and accelerating toward a singularity but not yet wholly unrecognizable. In some sense, the Big Crunch would be the most dramatic ending because it would be the most abrupt. The universe would have barely begun to cool before it turned around and ran in the opposite direction. Whether this is the universe's actual fate remains, as I have said, uncertain. But the conversation has changed. The DESI instrument and its successors, along with the Vera-Rubin Observatory in Chile and the Euclid Space Telescope, will be gathering data over the next decade that will dramatically sharpen our understanding of dark energy's behavior over cosmic time. The possibility that we are approaching a major discovery about the nature of the universe's ending is not idle speculation. It is a reasonable scientific expectation given the current state of the evidence. Part 10. What physics cannot tell us. Every scenario we have discussed tonight, the heat death, the big rip, the big crunch, vacuum decay, ends at a boundary. Either the universe enters a state of maximum entropy from which no processes emerge and continues existing as an increasingly empty and structureless field for unlimited time, or the universe terminates in a physical singularity, a point where the equations we use to describe it break down and cease to give meaningful answers. And in either case, physics is left without a description of what, if anything, lies beyond. Not because physics is insufficient as a discipline, but because the question itself is located outside the domain that physics, as currently formulated, is designed to address. Consider the heat death more carefully. The universe in heat death is not empty in the literal sense. It contains photons and leptons and the residual quantum noise of the de Sitter temperature. It expands forever. Given the Poincare recurrence time, a number so large that even writing it requires scientific notation to be practical, random quantum fluctuations will eventually recreate any possible configuration, including the configuration of the entire observable universe in its current state. This is a precise result from statistical mechanics. If the universe exists for long enough, it will, with certainty, spontaneously fluctuate back into something resembling its current state, complete with galaxies and stars and planets, and apparently observers. This is the Poincare recurrence theorem, and it applies to any system with a finite number of states, which a finite universe with a finite entropy bound may qualify as. The recurrence time is staggeringly large, a number with so many digits that writing it out in the usual notation is impossible in any practical sense. But it is finite, and in the heat death scenario, the universe has forever, which means recurrence is not just possible, it is guaranteed. This tells you something about the difference between impossible and merely vastly improbable, but it does not tell you whether anything genuinely new can emerge from a universe in heat death, or whether the fluctuations are purely formal, mathematical consequences of the theory that have no physical significance. The Boltzmann brane problem, which is the observation that random fluctuations in a heat death universe will eventually produce momentary observers with false memories, is considered a serious problem for cosmological theories, precisely because a theory that predicts fake observers outnumber real observers is a theory that undermines its own credibility. If you are equally likely to be a Boltzmann brane as a real observer, how can you trust your own observations? The resolution of the Boltzmann brane problem is an active area of research in cosmology and philosophy of physics. The singularity endings, the big crunch and the big rip, raise a different kind of challenge. General relativity, the theory that predicts these singularities, is known to be incomplete. It does not incorporate quantum mechanics. And at the scales of density and curvature involved in the final moments of a big crunch or a big rip, quantum gravitational effects are expected to become critical. Loop quantum gravity, string theory, causal dynamical triangulations, and other candidate theories of quantum gravity all predict that the classical singularity is replaced by something else, a bounce, a transition, a different kind of geometry. What that something else is differs dramatically between frameworks, and none of the candidates for quantum gravity has been confirmed by experiment. The big crunch and the big rip are classical predictions that we know must be wrong in their details at the singularity. What replaces them is genuinely unknown. What physics can tell us with considerable confidence is the broad shape of the future. The stars will die, the stelliferous era will end. Matter, if protons decay, will dissolve into lighter particles over timescales that dwarf the current age of the cosmos by more than 30 orders of magnitude. Black holes will evaporate via Hawking radiation, and the universe will reach one of the states we have described, whether that is heat death or something driven by the evolving character of dark energy. What physics cannot tell us, and what no physics currently on the table is equipped to tell us, is what lies on the other side of a singularity, or whether a heat death universe eventually gives birth to something new, or whether the laws of physics that currently govern reality are the same laws that will govern it in states so different from anything we have observed that extrapolation may be meaningless. The honest answer to the question of what happens at the very end of the universe is that we do not know. And the honest reason for that answer is not ignorance in the pejorative sense, but the more profound recognition that the end of the universe, in whichever form it takes, is located at a boundary of applicability of our current best physical theories. We are standing at the edge of the map, looking outward into the unmarked territory, and the arrows have run out. Part 11. The Last Light. Let me take you through the universe's future one more time, but this time more slowly, more intimately. I want you to feel the weight of the time scales, not as abstractions, but as real intervals in the life of the universe that has been your home. Right now, tonight, the universe is 13.8 billion years old. The cosmic microwave background fills all of space at a temperature of 2.725 Kelvin. Galaxy clusters are the largest gravitationally bound structures. Stars are forming at perhaps 3 solar masses per year in the Milky Way alone. The universe is actively producing light, actively producing complexity, actively doing all the things that allow life and thought and wonder to exist. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core. The red giant phase will begin. Earth's oceans will evaporate. If any descendants of life persist anywhere in this solar system, they will have known for billions of years that this was coming, and they will either have found another home or they will be gone. The Milky Way and Andromeda are already on a collision course and will merge into a single elliptical galaxy in approximately 4.5 billion years, well before the Sun dies. The night sky in 4 billion years, if anyone is here to see it, will be spectacular, full of new star formation triggered by the collision. In approximately 100 trillion years, 10 to the 14 years, the last red dwarf star will exhaust its hydrogen and cool to invisibility. The stelliferous era ends. No new stars will ever form again. The universe contains white dwarfs, neutron stars, brown dwarfs, and black holes. Galaxies still exist, held together by gravity, but they no longer glow. Over the following trillions of years, white dwarfs cool toward black dwarfs. Brown dwarfs continue their slow contraction and cooling. Neutron stars spin down. Black holes continue to grow by absorbing whatever matter comes near them. Occasionally, 2 stellar remnants merge, producing a brief burst of energy, a momentary flash in an otherwise dark cosmos. Between 10 to the 34 and 10 to the 40 years, proton decay, if it occurs as predicted by grand unified theories, dissolves all ordinary matter into lighter particles. Every white dwarf, every neutron star, every brown dwarf, every rock, every grain of dust is chemically disassembled by the slow but cumulative probability of proton decay. Matter as a concept becomes inapplicable. The universe contains black holes and their Hawking radiation, and almost nothing else. Between 10 to the 67 and 10 to the 100 years, black holes of various sizes evaporate via Hawking radiation. The smallest go first, briefly becoming as hot as the surface of the Sun before their final explosive evaporation, a momentary flare of energy in an otherwise featureless cosmos. The largest supermassive black holes take longest, burning at temperatures so low they are imperceptible by any physical means, but losing mass steadily until, in their final moments, they too release a burst of radiation and vanish. After 10 to the 100 years, the last black hole is gone. The universe contains nothing but an incredibly thin, incredibly cold, incredibly diffuse gas of photons and leptons expanding through space at a temperature of perhaps 10 to the negative 30 Kelvin. The cosmic microwave background has by this point been redshifted to wavelengths longer than the diameter of the observable universe. The universe is effectively at heat death. Entropy is at its maximum. No ordered processes occur. From this point forward, assuming the universe survives as a heat death rather than terminating in some singularity, time continues but without any event to mark its passage. There are no clocks because clocks require ordered processes. There are no observers because observers require complex, organized, low-entropy systems. There is only the quantum noise of the de Sitter vacuum, a cosmic hum at the minimum possible temperature, fluctuating in the way that quantum systems always fluctuate, producing nothing that any mind could ever observe or any measuring device ever record, because the minds and the devices are gone and cannot be reformed from the level of entropy that remains. And then, at some time so remote that the number expressing it is longer than any text humans have ever written in all of recorded history, a fluctuation occurs. A fluctuation large enough to locally reduce entropy, to assemble from the thermal noise a structure more ordered than its surroundings. The structure might be a single complex molecule. It might be a whole brain with false memories and a moment of consciousness. It might be an entire galaxy, a copy of the Milky Way, assembling itself from thermal noise and existing for a brief cosmological moment before dissolving back into the background. The probability of each of these is incomprehensibly small. The time scale on which they occur is incomprehensibly large. But in an infinite or effectively infinite future, nothing that is merely improbable is impossible. The Poincaré recurrence theorem guarantees that if the future is long enough and the system has a finite number of states, every state will eventually recur. The question is whether these recurrences constitute a genuine resurrection of complexity or merely a mathematical formalism that does not cash out in any physically meaningful way. Physics does not answer that question. We do not know whether the recurrence theorem applies to the universe as a whole in any operationally meaningful sense. We do not know whether a Boltzmann brain experiencing a moment of apparently coherent thought in a heat-death universe is in any relevant sense conscious, or merely a physical system that momentarily satisfies the formal criteria for complexity without the context, the history, the ongoing continuity that makes consciousness what it is to a conscious being. These are questions that physics formulates but cannot currently answer. They belong to the intersection of cosmology, statistical mechanics, philosophy of mind, and the foundations of physics, and that intersection is one of the most genuinely open and genuinely important territories in all of human knowledge. Part 12, What the Ending Means. I want to come back to you now. Sitting wherever you are sitting, in whatever time of night or day this happens to be for you, and I want to offer the thing that the block universe, the thermodynamic arrow, and the physics of the ending all point to in their different languages. The universe is going to end. That is not a metaphor. That is not a poetic statement about impermanence dressed up in scientific language. It is the actual, literal conclusion of the best physical theories we have, confirmed by the best observations ever made, pointing to a real physical terminus that the cosmos is moving toward, and that no process within it can prevent or reverse. The stelliferous era is finite. The degenerate era is finite. The black hole era is finite. Even the heat death, if we are generous and call it a continuation rather than an end, is a state from which no further meaningful structure, no further ordered process, no further anything that we would recognize as the continuation of the cosmos can emerge indefinitely. The universe is running down. The second law of thermodynamics, which is not a law in the sense of a rule that could be broken, but a statement about the statistical structure of physical systems with more possible disordered states than ordered ones, is relentlessly and irreversibly carrying everything toward its maximum entropy state. Most people, when they encounter this fact, feel one of two things. Some feel what I would call the vertigo of scale, a kind of intellectual nausea produced by the collision between the brief, warm, meaning-saturated world of human experience and the cold, vast, indifferent timeline of the cosmos. We live in a universe that has been burning for 14 billion years and has perhaps another 100 trillion years of starlight left, and then trillions of years of cold remnants, and then googles of years of slowly evaporating black holes, and then heat death, and the response to all of that from the perspective of a creature whose entire civilization fits into 10,000 years of recorded history is something that does not have a comfortable name. It is not quite fear, and it is not quite grief, and it is not quite awe. It is something at the intersection of all three, something that requires sitting with for a while before it settles into anything usable. Others feel something closer to relief, not because the universe's ending is comforting in any ordinary sense, but because the scale of it, properly absorbed, puts the scale of human concern into a perspective that is genuinely clarifying. If everything ends, and the ending is so vast and so slow and so indifferent that no particular ending within it can claim special cosmic significance, then perhaps the question of what to do with the brief, bright, improbable window of ordered complexity that you happen to be experiencing right now is more clearly a question for you to answer than a question for physics to settle. Physics describes the structure, physics describes the timeline, physics describes the ending. Physics does not describe what to do inside the ending because physics is a third-person description of reality, and the question of what to do with an existence is an irreducibly first-person question. Einstein, in his later years, thought carefully about the relationship between the physical picture of the universe and the experience of being inside it. He wrote, in a letter to the bereaved family of his oldest friend Michel Besso, that the distinction between past, present, and future is only a stubbornly persistent illusion. He meant by this not that experience is illusory in the pejorative sense, but that the block universe, the four-dimensional structure in which all events coexist as permanent geometric features, means that nothing is lost in the deepest physical sense. The moments that have happened are, in the geometry of space-time, as real as the moments that are happening now. They do not disappear into the past. They are simply at different coordinates. The warmth and life and brightness of the stelliferous era, which is the era you are living in, is a real and permanent feature of the four-dimensional structure of space-time, exactly as real as the cold and dark of the heat death will eventually be when it, too, becomes a feature of the same structure. This is not consolation in the ordinary sense. It is not a promise of continuation or a guarantee of preservation of anything you personally care about, but it is something. It is the recognition that the universe is, in its entirety, a complete thing. It has a shape. It has a structure. It has a beginning that we can observe the afterglow of, and it has an ending that we can calculate. And between them it contains the extraordinary, improbable, temporary fact of complexity, of organization against entropy, of stars and planets and life and minds that can look at the structure and ask questions about it. The universe is, from the outside, a complete story. The heat death is the last page, and every prior page, including the one you are currently on, is permanently part of the book. Stephen Hawking spent years thinking about the thermodynamic arrow of time, about why we remember the past and not the future, about why the universe's entropy is increasing and what that means for the nature of time itself. Roger Penrose has spent decades thinking about what comes after the heat death, developing his conformal cyclic cosmology, a framework in which the distant future of a heat death universe is mathematically equivalent, through a geometric transformation, to the initial conditions of a new Big Bang, suggesting that the universe might cycle through infinite aeons, each ending smoothly becoming the beginning of the next. The model is speculative and contested, but it represents a serious physicist's attempt to grapple with the question of what lies beyond the ending, and the attempt itself is significant. We cannot help asking, even when the question is at the edge of what our tools can address, we build new tools and push further. There is something worth saying about the DESI measurements and the other new data that has complicated the clean heat death picture. The fact that dark energy may be evolving, that the fate of the universe may not be settled in the way we thought, is not a frustrating uncertainty but a genuine scientific frontier. The universe is telling us something we do not yet fully understand about its own future. The instruments being built right now, the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, the European Space Agency's Euclid mission, are gathering data that will substantially sharpen our understanding of dark energy over the next decade. It is not implausible that within the lifetime of people currently doing physics, the broad question of whether the universe ends in heat death or in something more dramatic will be narrowed to the point where a confident answer is within reach. That is a remarkable situation for science to be in. The question of how the universe ends, which for most of human history was either a religious question or a purely speculative one, has become an experimental one. We are measuring dark energy. We are watching it evolve or not evolve with instruments of increasing precision. We are running simulations, building models, testing predictions against observations, doing what science does. And the universe, so far, is giving us enough information to work with while withholding just enough to keep us working. It has not yet decided to tell us definitively how it ends. It is letting us figure it out. Part 13, the physics of the last moment. Let me take one final pass through the physics, because I think the most extraordinary thing about all of this is not the scale or the darkness or the thermodynamic inevitability. The most extraordinary thing is that we can calculate any of this at all. That the laws of nature, which we worked out by dropping balls and splitting atoms and building particle accelerators in the span of a few centuries, extrapolate with reasonable confidence to describe what the universe will be doing 10 to the power of 100 years from now. That the same equations that allow you to navigate by GPS and that explain why the sky is blue and that describe the orbit of the moon also describe the evaporation of the last supermassive black hole in the final cold era of the universe. The universality of physical law is not a modest claim. It is arguably the most remarkable discovery in the history of science. And what the laws tell us about the final physics of the universe is this. The second law of thermodynamics is not going to be repealed. Entropy will continue to increase until it reaches its maximum value, and there is no mechanism within the framework of physics as we currently understand it that can reverse this direction over cosmological timescales. The universe is moving from order to disorder, from concentrated energy to diffuse energy, from the improbable to the probable, and it has been doing so since the Big Bang, and it will continue to do so until the maximum entropy state is reached. This is the ending that physics considers most likely, given that dark energy is approximately a cosmological constant, heat death. But the physics also tells us something else that I think is worth holding. The laws that describe this ending are the same laws that describe you. The second law of thermodynamics is the reason you age, and the reason your coffee cools, and the reason the universe dies. The quantum mechanics that makes Hawking radiation real is the same quantum mechanics that makes chemistry possible, and makes DNA stable, and makes neurons fire in patterns that constitute thought. The general relativity that describes the geometry of space-time around a dying black hole is the same general relativity that makes GPS work and that Einstein worked out while thinking about falling elevators in Bern in 1907. The laws of physics are not external impositions on a reluctant universe, they are the universe describing itself. And the universe describing its own ending with the same equations it uses to describe its own beginning is doing something philosophically extraordinary. It is being honest about what it is, all the way to the last photon. The universe began, as far as we can tell, in an extremely low entropy state, a hot, dense, almost perfectly uniform plasma that by some mechanism we do not fully understand was in the most improbable configuration possible for its energy content. It has been running down from that improbable state ever since. The stars are how it runs down. The stellar life cycle is entropy increasing. The heat you feel from sunlight is entropy increasing. The complexity of life, which looks like entropy decreasing locally, is paid for by an enormous increase in entropy in the sun that powers it. Everything is the second law. Everything is the universe moving from where it started, which was impossibly ordered, toward where it is going, which is maximally disordered. And in between, briefly and improbably, there was organized matter that could ask why. The cosmologist Sean Carroll, who has written and thought about the arrow of time and the thermodynamic structure of the universe as carefully as anyone alive, frames it this way. The existence of conscious beings, of observers, of anything that experiences the universe from the inside rather than merely being part of the physical furniture of the outside, is a direct consequence of the universe being in a state of intermediate entropy, far from its initial low entropy state, but not yet at its final high entropy state. We exist in the middle. We exist in the window between the improbable beginning and the thermodynamic ending. The window is long, it spans trillions of years of stellar activity, but it is finite, and we are in it. And the fact that we can be in it, and notice that we are in it, and calculate how long it will last, is what physics looks like when the universe generates the right conditions for complexity.
Part 14, a final reckoning.
The universe will end. We do not know exactly when, and we do not know exactly how, but we know it will end, and we know broadly what the ending will look like, and we know what physics it will obey. The stars will exhaust their fuel. Matter will decay. Black holes will evaporate. The cosmos will become cold and dark and empty. And if dark energy is evolving, if the DESI hints are confirmed by future observations, the timeline and the character of that ending may be very different from what the simple cosmological constant model predicts. But the ending comes. What physics offers in the face of that fact is not comfort in the religious sense. It does not promise continuation, reunion, survival of identity, preservation of what matters to any individual human life. What physics offers is precision. It tells you with extraordinary confidence that the universe is a complete thing with a shape that spans from the Big Bang to the last photon of Hawking radiation, from the last black hole, or to the Big Rip, or to the Big Crunch, or to whatever termination eventually arrives, and that every moment in that shape is as real as every other moment. The low entropy, extraordinary morning of the universe, the stelliferous era, the era you and everything you have ever known are a part of, is not made less real by the fact that it is followed by a long, cold, dark, and increasingly simple future. It is exactly as real as any other part of the structure. The block universe is indifferent to duration. Short does not mean less real, and there is this. The universe, in the brief window of its stelliferous youth, produced exactly one known example of matter that could look at the whole structure and describe it. One known example of complexity high enough that the equations could be written down, the observations made, the calculations performed, the question asked, how does this end? That is remarkable by any standard, that it happened at all in a universe that has no obligation to produce such things, that the laws of physics contain within them the possibility of complexity sufficient to understand those same laws, is a fact about the universe that no physical theory is required to explain, and that no physical theory is capable of explaining. The universe is self-describing, not everywhere and not always, but here and now and briefly. And that might be the most remarkable fact about the cosmos that physics has ever uncovered. The fire is burning. It will not burn forever. But right now, tonight, in the only window in the universe's history in which such a thing is possible, something made of stellar ash is sitting somewhere comfortable, listening to the story of how the fire will eventually go out and wondering what it means. That is the stelliferous era. That is where we live. And whatever comes after the last star, whatever physics eventually describes at the thermodynamic end of everything, this moment, this wondering, this asking, is as permanent as any coordinate in the four-dimensional geometry of space-time. It was always going to happen, and it will always have happened. Even after the last photon of Hawking radiation has dispersed and the universe has reached its maximum entropy, and there is no structure left anywhere to observe or to wonder or to ask anything at all. The universe ends. The question of how to live inside that ending remains, as it always has, yours. That is what physics says. Sleep well.